The textbook's really good too. Okie dokie. Well, welcome everybody. This is the last time that we get to be together before the final exam. And the hope today is that we will cover in enough depth that you'll have an idea of how to handle a little bit more information from tables that you'll find online for descriptions of how the elastic curve will behave, the deflection across the beam. I hope that superposition will be something that you enjoy and you remember. Indeterminate systems are always tricky, and so hopefully also that we'll shed some light in terms of how to think about them, namely that we have to make sure that we understand that equilibrium is not alone, or itself alone is not enough to solve the problems. And then we'll talk a little bit about beams as springs. Time permitting, I also hope that we can have a little bit of a discussion about what we've covered over the course of the semester, and hopefully leave with a sense of, okay, why did we cover these topics? Why are they important? And I don't know, I hope you take my word for it that you will see these topics again in subsequent courses here at Rutgers and as engineers in the future. Okay? So, administratively, here is the syllabus, and it's just hard to believe that another semester has gone, and we are finding ourselves at the very end. So the final exam is going to be a week from today, and it's going to be here and on College Ave. If you'd like to switch to College Ave, please send Proj and me a message over Canvas inbox, and we can facilitate that. There's plenty of space on College Ave, plenty of space. Note the exam is at 8 a.m. Okay, I do often wake up early. Unfortunately, on an exam day, that's not really fun for me either, because often there are last minute things that have to happen, including printing the exam. So I will most likely be up very early that day. We will have a couple of office hours. Okay, I'll send out some messages about them. Probably Friday, probably Monday. Okay, we'll see. I'll take a look at my schedule and I'll get back to you on that. But of course, today is the last time we meet. Tomorrow is officially the last day of classes. And so we're going to have the labs be due tomorrow at midnight and the last assignment be due tomorrow by midnight as well. One of the videos, there are only two, well, actually, I guess there are three questions because we have the finite element question that I moved to tomorrow night. Okay, but that video is already up. And so is one of the two remaining questions. They're both, those two are up. And I have one more that I'll post this afternoon. So you should be all set in terms of having the extra helps for being able to do those problems. So please get those things in by tomorrow at midnight. Okay. Exam 2, yes, it took us a little while to get it graded and back. The exams will come. They will be delivered by our wonderful TA, Proj, in a few minutes. And so we'll be able to distribute those at the end of the class. Okay. Any questions administratively? Any questions? Anything you'd like to bring up? Okay. As we were discussing kind of just casually a few minutes ago, the advice for the exam, the final exam, I think is again the same. Please look at the previous exams. Please look at them. Please review them. If there are things you don't know, if there are steps that I would expect there to be questions on the steps on how to go from, this to this to this. Send a message in the group me. Send me a message over Canvas. Okay, we got some time. Try to communicate and work through any bugs that there might be. I will say that if you go all the way back to 2015, there are still some bugs in one of those exams. Okay, based on some of the beam bending stuff that we're, I think, covering today. So if there are a couple things that look a little funny on boundary conditions, it's okay. The solutions were a little bit wonky, and I haven't gotten back to fix them. There may be other issues. If you have other questions about the solutions, just send me a message, okay? And we'll hopefully be able to clarify anything that you're struggling through. Okay? I do want the learning to continue. Okay. Okay. Thank you. There they are. All right. And the exams, right? Your grades have been posted. The average was about 11, and average, generally speaking, will be B-ish territory. Okay, for the whole class. Okay. Let's go. So our objectives today are to discuss superposition yet again, but now in the context of beam bending. And we will also discuss indeterminacy and indeterminate systems. So in some respects, these topics will be a bit of a review of the types of things that you've seen previously. Okay? And then the last topic will be thinking about beams as springs. Okay? And yeah, so if we could just tone it down a notch upstairs. Thank you. All right, awesomeness. Okay, so why, maybe I haven't, I'd just like to emphasize for just a couple minutes again why these topics are so important. Okay, now, many of these things will be in tables. Okay, so when it comes to understanding what the elastic curve looks like, you should, if it looks somewhat familiar, okay, I don't think as an engineer you're often going to be asked, unless you're trying to get the job interview or the job. That you'll be asked. You may be given this type of sketch and go ahead and tell me what the bending stress is and what the it'd be a stretch, I think, for most job interviews to ask you to calculate the deflection curves. But handling beams is something that you want to be able to do, right? But you may find yourself designing a particular tool or thinking about the end effector on a robot and how much it's going to be deflecting downward based on the weight that might be distributed across it because of the gravity acting on that arm, or the type of load you're picking up. And just having this kind of general concept of, oh yeah, the bending stresses are going to be the highest here at the torso, or where the arm connects to the rest of the body, to the torso. Having an idea of where I can look to find out what the bending stresses are. Knowing the flexure formula, right? A lot of that will probably be primary. But then, yes, there are going to be situations where you've got, for example, when I was an intern, and I wasn't so concerned about the masses that I was working with, but I had a robot with an end effector that was trying to get wafers into a cartridge. And so a cartridge is essentially just a stack that holds a lot of wafers in it. So maybe like 20 wafers. And so I had my job as an intern was to figure out some procedure to calibrate the end effector of the robot to the location of the cartridge, all right? So that then we could put the wafers in appropriately, okay? Or there was another one where we were looking at trying to get the end effector into a special chamber, and so it had to get through the door appropriately. Again, techniques for being able to tell the robot where is the position I want to be. So when you have this end effector, it's real. You start to see things and you're like, wait, that end effector is not really perfectly horizontal. It's a little bit down. And how's my camera going to be looking? And how am I going to be thinking about what marks, what fiducial marks, as you might call them, as we call them, can I use for my images to know where I can place my stuff? And this was like 20 years ago. And so these issues, they haven't gone away, all right? We have maybe more complex algorithms and things, but being able to figure out what the displacements are, what the deflections are, is going to be a long-term problem, right? You think about which types of careers can you enter and be assured that you'll always have a job? I think of things like cooking and cleaning, right? Many of the services, well, actually cleaning, we're working on cleaning robots, so maybe not as much. Maybe there'll be a lot of robots doing cooking too. Okay, so maybe not the best idea, right? But there are lots of professions, I think, that are going to be around, including engineering. And so having these concepts ingrained will be helpful. Understanding that this type of system is probably determinate in that, I can't really take anything away in terms of constraints and it still be statically in equilibrium, right, without doing something like that. But understanding that indeterminate systems, you have things interacting with each other, and that creates an interesting, quote, tension. Okay, that makes it more complicated to solve, and I need to know something about the material properties and the elasticity of the system to be able to determine what the loads inside the structures are. And then springs, we've talked about the washing machines the last time. I think from diving boards to car parts to shelves, all these types of things, from even tables, although those are more like plates than beams. We want to make sure that these items that we might be designing, whether they're for the aerospace industry or for the home or for other commercial applications, that they deflect and they deform as we expect them to do so. And that's where, of course, the finite element is also useful. All right, so that's enough on the importance. And last time we also talked about fluttering, right, on airfoils. And so that's another reason where you would like to know what the spring constant is for a particular structure. Okay, so remember this. We've talked about superposition a couple of times, session 3 and 16. The superposition principle is essentially that for linear systems, the net response caused by two or more stimuli is the sum of the responses. A very useful principle. And we see here, F1, get a delta 1, F2, get a delta 2 for this bar that we're extending. And we can say, well, if I had F1 plus F2 acting there, then the deflection or the extension would be delta 1 plus delta 2. Same exact slide that we've introduced previously. Now, how do we do this with displacements and beams? Okay, we need to not just consider. So the nice thing about the bars is that in many cases it's just extension, right? But do you remember that problem probably in session 4 where we had those bars hanging and there was a rigid beam and then there was another bar hanging and that rigid beam would rotate? We didn't even say it would deflect, right? But it would rotate, and then that made everything a lot more complicated, right? And there's a whole Python script to handle that issue. Okay. We have just in a regular beam, we have now understood from the last time we met that it's not just displacement, but it's also slope that we have to keep account or track. Okay. So for that type of situation, it can be important to remember, when I have a member that's at an angle, even if there's no additional deflection, okay, like in deformations, like there's no curvature here, right? If I have a slope at this point and there's no additional curvature, this point obviously is lower than this point, okay? Or this point is going to be higher than this point, okay? But I can calculate that out. I can figure out how high or how low it is based on the angle at this joint, okay? So when we do superposition, it's not just going to be, okay, add this displacement to this displacement to this displacement. It will also have us think a little bit about, okay, where is that endpoint which is out there? Even though, as I say, I guess, there are often members that have zero bending stress, zero shear stress in them, and they're just along for the ride. But geometrically, being along for the ride has significance. So we'll be able to look at some of these, sum of individual displacements. We'll have to account for the slopes from the individual loads, also to get overall displacement. So here is a beam that has two loads on it, P and Q. These are concentrated forces. And if we want the displacement at the end, well, how would you go about breaking this up? Just quickly, how would you go about breaking this up into a problem that's maybe a little simpler? I want the displacement at the end. Yes?
Break it up into two sections, so you do the deflection for either section of L and
Okay. So that's an interesting. Okay, so that's one way to do it. Now let's think if I have tables. All right, and I don't want to do like I have tables, right? So I have like the little expressions that tell me the deflection, right, along the beam, and I also have tables that show me the slope. And I don't want to do any equilibrium. I don't want to do any equilibrium. Now, how would you take this thing and break it down? So, right, you don't want to do the method of sections if you don't have to. Yes?
deflection by P and then deflection by Q.
Right. So exactly, right? So I could look at the system in terms of the deflection at the end, okay, due to P, right? And then also look at the deflection at the end due to Q, all right? And if I have tables for those two values, I'm kind of done. Now, if I don't have, it's possible now I only have one table value or one table for this, okay? And I'll just verbally say something that you probably won't get at this exact moment, but it will become more clear in a few minutes, okay? Very soon about how to take care of slopes. Do you see that this region right here, I'm going to say that's along for the ride. Okay? Yes, I have a displacement here at this end, but just like we were saying, there's no internal shear force from L/2 to the end. You can see that, right? If I just did a quick method of sections and I covered up the left side, right, I'd say, well, there's nothing going on in there. Okay. So let's just say that all I had was a cantilever beam table, right? All I have is this one. And maybe it's a whatever R or something I'm putting on the end, right? That's the only thing I have. But if I know the slope at the end of a beam, I can think of this as being the end of the beam, and I can know what the slope is, and I can know how much that's deformed. I can know how far down this delta is at L/2, and I can know the angle that it's got, the slope that it has at this, I'm backwards from you all. I could know the slope that it's got at that L/2, and so then I would be able to figure out, right, just by using the fact that I've got a slope and I've got some length in either trigonometry or geometry to figure out what the additional distance that I've gone down might be. Okay, and so again, this is taking into account displacements that account for slopes from individual loads. Now, it's possible that I may just have a table that shows the deflection here at the end with a load P applied in the middle or at different places along the beam. In that case, I don't have to do all that work, all right? But what we're trying to get here is that there are ways to essentially kind of not cheat, but not do the EI second derivative of little v versus x equals m, all those calculations if you already have done tables, right? In a cliche way, we're trying not to reinvent the wheel every time. That's what we're doing. Okay, so here we can say that delta is equal to delta P plus delta Q. All right, and if this were a table, okay, so here is a table that we've discussed, and all these well, not all of them, but many of these that have these beware. All right. If you remember, and I talked about this a little bit on the homework, that our convention that we use, our convention that we've been using actually, look. Ah, okay, it's kind of a straight line. Okay, it would actually, if this were the moment, okay, it would actually be down at minus PL to start, and it would go up to 0. Okay, and the line for the Q, okay, this would actually be, this is a little confusing too because I don't think they're even self-consistent here with this particular plot. This would be flipped. So this would be a positive. This would be up here. So you would have something like that. Okay. So the Q is really our big V, and if we're plotting this out, this would have positive value P. Okay. You can go ahead and you can do it either by the differential integral method, or you can do it through the just equilibrium. All right. This is something you did back in statics. Okay. So this should be pretty familiar. Displacement, we say that displacement is positive in the upward direction, so we would also kind of say that these values from our convention would have negative signs in front of them. Okay, we would say that really this is like a tiny little v. Okay, and that's positive upward, so these would be downward. So just be careful here. We need to use a little bit of our intuition to know, oh, okay, that's a positive value, is that a negative value? And now we're talking about superposition. So, you know, depending on which way you draw the arrows, you might add certain things to each other, displacements to each other, or you might subtract one displacement from another. Okay? And I think that will become clear also in the homework that's due tomorrow night. Okay? So just, I've said it before, you know, one of my wishes as an undergrad and still now is just like, tell me which direction is up, which direction is down, and which direction is positive, and which direction is 0 or negative, right? Those simple things, if I just know which direction is which, they make your life a whole lot easier. The corollary to that, though, is don't get too hung up on that on an exam, because in reality, usually we don't pay that much attention. I mean, you'll get a little bit of credit knocked off, but it don't get stuck on that point. Just commit. You got to commit sometimes and then go, right? Because if you can think about it for half an hour, but it's not worth half an hour of your time, and that's the sad thing. Okay, but real people who design products and things that have to work, not get credit on exams, of course, right? They think about these things, and there are mix-ups and issues that happen when people don't get the signs right or people don't get the units right. There's that famous metric mix-up between JPL and NASA on Mars, and that's a unit thing, just a unit thing, right? So we want to keep that straight. Okay, so superposition on a cantilever, right? Same problem. Now let's go into a little bit more detail of how this works. So we're going to, once again, say, all right, I want to know what the delta P is, or the delta due to that P at the end of the beam, even though P is not at the end of the beam. And we want to know what the delta Q is, even though the Q is, the Q is right on top of the delta Q. So anyway, it's not really that relevant. But this one, you can kind of see, is exactly like this, right? Everyone hopefully can see that. So that Q, I just pop in Q, and that's my displacement at the end from Q. All right? I mean, yeah, and I mean, of course, this is a little v max. That's how we often write it, okay? And, you know, we would write this as the little v as well, okay? It's important, though, to be able to take information from tables, and even though it's not using exactly the same thing that you've got, you know, in a textbook or you've seen before, that you can, you know, infer. And I think that's one of the things that's also probably a little bit hard about this class is that you know, if you look at the previous exams, right, they're either, some of them are hand drawn, right, or they are you know, just pretty simple diagrams. No like shading, no like real fun things right from a textbook. But I don't know. I think some of us, if we saw the textbook problem, it'd just be soothing and comforting, and we'd get less stressed or something. All right, but it's important to be able to make that jump. So now, this expression right here, where did this one come from? This one comes from right here. Okay? So this is the px squared times quantity 3L minus x over 6EI. This is just for the cantilever, right? So once again, we write it out, and that's the expression. And notice I didn't put the negative sign there, so I just got to be careful. Okay, I just got to be careful. I know that's going to be downward, okay, for this particular problem. This is not just the max. That's another thing to be careful about. This is the elastic curve. This is as a function of x. Note, this is maybe a little bit smaller here, right? But oopsie-doo. Okay, so you see here, let's say that I wanted to know theta at any location, but maybe at the end of the beam, okay? Notice, for theta, that's slope, I need a d little v with respect to x. Is there any x here? No. You cannot calculate the slope with just this expression. We have to use this expression instead, okay, to take the derivative of the v with respect to x. So that's something to keep in mind as well. It'd be nice, all right, but you cannot do that. All right? I don't know if I told you the story, but our oldest daughter, when she was very little, she started talking, as kids do, and we were not pleased when one of her first songs that she composed was, "You cannot do that. You cannot do that." So we're like, oh, what kind of parents are we? That's what she's getting, all right? Lots of, you cannot do this. Of course, we want her to feel like she can do things, okay? Anyway, so, but we'll say that please use this one instead, okay? The theta, so we can go ahead and take the derivative of v with respect to x, and we can work that out, and we get this expression right here. Why are we doing that? Because we said if we're only given that one table, we need to know what the slope is here, and then be able to figure out what the portion that's along for the ride is doing in terms of its decrease in height, or increase in displacement, if you will. All right. So now, if we want, we can figure out what the theta might be at this right end. Okay, so theta of x equals L is going to be this. So that comes from plugging in L here and L there and getting this expression. Right, so this is essentially 1 PL, or 1 PL squared, and this is minus 1/2 PL squared, so we get half PL squared over EI. So here's just kind of a little diagram. I can think of having this delta 1 that's right underneath P. Maybe it would have been better, I don't know. I call it delta P because we were talking about superposition, right? But this is like maybe delta P1, whatever. But it's right at L over 2. So in order to calculate out what's happening here, what do you think I should do? To figure out the delta 1, how do I figure out delta 1? Do you feel like you have enough information to figure out delta 1 on this slide? I don't want you to do any integration, nothing fancy. I just want you to tell me, what is delta 1? How do you figure out what delta 1 is? Yes? Thank you, right? So you come over, now where do you plug in L over 2? This is a shortcut. You might be tempted to do it here. Do not do that, okay? Where did you mean to plug in delta over 2? Okay, so yes, okay, so, okay. This is why we're doing this, all right? Notice, if I have this equation, this is for the cantilever beam. All right, these V of x and theta of x are with the cantilever beam with the load at the end. If I plug in L over 2 right in here, that is telling me what the deflection is in the middle of this beam that has the load on the end. Okay? So I agree we need to plug in L over 2 somewhere, but where do we plug in L over 2? We're just interested, for now, I'm just interested in delta 1. Right? So it's as if there's nothing over here. This part of the beam does not exist for this delta 1. So where do I plug in L over 2? Let's say that this beam is 2 meters long. And so I want to be at 1 meter. And this is now a beam, really essentially, from here, it's just essentially a cantilever beam of 1 meter. And I want to know what the deflection is at the end of that 1 meter beam. Which equation do I use to figure out what the deflection is at the end of that beam? And for x equals 1 meter. Yes? Okay, normal beam bending, yes. Yes, Brennan.
So L equals L over 2, and then X is just the total L over 2.
Yes, and so which equation? Of the ones that you see up here, which one would you use? There are 1, 2, 3, 4, 5, I guess. Or actually, this is repeat. So there are like 4 equations. So which ones of these would you use? The fourth? I'm going to give you the benefit. That's this one right here, right? Okay? Let's point this out. This equation is when we plugged in the total length of the beam, L, right? And this equation is the maximum deflection at the end of the beam. All right? I have now essentially taken this problem to be an entire beam, but it has length half of what it used to have. Okay? Do you see this? This is important. You want to be able to visualize this a week from today. Okay? Because people will plug in L over 2 into one of these 2 equations. But do you see how plugging in L over 2 into these equations is just taking this problem and figuring out what the displacement is here? I don't want to know the displacement. I don't want to know the angle here. I want to know the angle here when Q is being applied on a beam that's half the original length. Okay? Am I making sense? All right, so you could do a couple of things. You could say, oh, I'm just going to plug in L over 2 here, and I can plug in L over 2 here, and L over 2 here, and that would give you the right answer as well. Okay, but you got to switch this L over 2, this L to L over 2, right? But this one, it's already done for me. This is the slope at the end of the beam as well. We're going to use that in a second too, all right? This one, not done for me, okay? This one is still using a beam of length L, not beam of length L over 2, okay? This one down here, like we said, this one will give you the maximum displacement, which is what you want for a beam of length L over 2. Okay, it's a little bit of a mind bender. Okay, this is maybe not how you think of superposition. It's an opportunity to expand. Okay, now, what's the other important quantity that we need here? Theta. All right, we need the theta. So, we got to be careful here when you calculate it out, because theta, right, it has like a negative slope. Okay, so just, whatever, you can say, well, I could, if it's a positive number, just make sure that, you're thinking that it's going further down. Okay, so you're going to add whatever you want to do. You want to get to delta P, you want to take this value and then add to the additional displacement that comes here. How do we figure out what the vertical displacement is? If I know this angle, how do I figure out what this additional? So this, from this gray line to this point here, how do I figure out what that value is? If I know theta. Yes, Stephen. Oh, it's okay. It's okay. This is the first time we're doing this. Others? Mark? Okay, so you can do it, yes, in terms of sine theta, all right, if you want. But sine theta equals what? Sine theta would be, so that would be equal to this opposite side, right, over this hypotenuse, right? And what's that hypotenuse? L over 2, right? That's the hypotenuse. Okay. Now, in reality, if you wanted to do tangent of theta, you could too, because these angles are typically small. Okay, so there's not going to be a big difference. So if you said tangent of theta, that's this divided by this length, and you said this adjacent side is about the same length as the hypotenuse, you would be fine as well. Yes, Jonathan?
Can you explain a little bit more what the difference is between theta L and theta x?
Sure. Theta x is going to be the slope as we go, okay, in particular, don't look at this one for a second. It's going to be the slope as we go along the beam. Okay, theta of x. And it has a very specific loading where the load P, or in this case Q, is at the end of the beam. All right, so that is here, if I were to use this equation, I need to make sure I take out this L and put in L over 2, because that is what the length of that's the overall length of the beam I'm interested in. This other portion is just long for the ride. Or I can shortcut and just come over to here where I've already defined my theta as theta at the end, okay, of the beam, and say, oh, it's not really L, it's really L over 2, and I plug that in here. So I'd have, just to be clear, that'd be P quantity L over 2 squared, so that's going to essentially divide everything by another 4, so I'd have PL squared over 8 EI. Okay?
Okay, and then also, you would be doing this twice, once for P and once for Q?
Not exactly. Well, yes, we will be doing the displacement for Q, okay? But for that one, it's at the end, and so we can just use, this equation right here and plug in Q with the L. All right, because look, what do we need to, let's see, we need to do a couple of things. We need, okay, if we go back, remember, our end goal is to figure out what the displacement is, the overall displacement is at the end. That is just equal to delta P plus delta Q. Delta Q is the easy one, all right? That's just the PL cubed over 3EI, okay? But we don't use P, we use Q. That's QL cubed over 3EI, right? But to figure out what the delta P is, that requires this extra nuance for the delta and the displacement at the midpoint. Okay? Hopefully that's clear. If that's not clear, please go back and understand this before Tuesday. All right? So here's now a little bit more detail. We need the displacement little v, or the delta 1, and theta, where the delta 1 is equal to PL cubed over 8, right? That's substituting the L is equal to L over 2 into this equation down here. And the theta 1, all right, that is coming from this equation where we've plugged in L over 2 over L, so that gives us the PL squared over 4, and that becomes PL squared over 8 EI. Okay? Clear? Or clear as mud? Okay? So, the hard part of the problem is over. Well, it's actually not quite over. Because now we need to figure out, okay, what is delta P? Delta P is going to be this delta 1 plus the L over 2 sine, okay, of PL squared over 8EI. Okay. Remember, the sine, right, is the opposite over the, so, right, this is going to be, really, we're looking at sine of theta is equal to I guess we could call it the extra delta along for the ride over the L over 2. Okay, that's what we've done. Yes, Brennan.
So just so as follows, are you saying that Q is perpendicular to the beam, or is it downwards?
It is downwards, okay? And for our intents and purposes, these angles are small, so we're going to assume that it continues to be orthogonal and downward at the same time, okay? For small angles. And this is one reason why large deformation becomes nonlinear very quickly, because you have to think, oh, is my force now still acting in the direction of gravity, which was up and down, but now it's not acting like that. It's not acting like that orthogonal vector that I had originally when I started. Okay. These are small deflections that I've exaggerated in this way. Okay. So, oh yes, and I guess I can write the word sine. One abbreviation is just to write S, but I'll go ahead and I don't mind writing out the word sine. Okay. Okay, so delta Q is equal to QL to the third over 3EI. You see, that is just the transplant from this equation down here, right? There's nothing funny happening here. Just Q for P, P for Q. Okay? So now I can add the delta P and the delta Q to each other, and that's going to be the overall displacement. Okay. Any questions? Concerns? Okay. So this is how to use superposition. So you've got, and you're like, it's just easier for me to go through the whole double integral thing. For some, sure, maybe. Okay, but maybe you don't want to do the whole double integral thing and look at it, because I mean, this is not a trivial problem in that you've got like an x1 and you probably have an x2 either coming from the other side or x2 coming from the same side or x2 starting in the middle. So you've got a number of things to negotiate to do this. Or you could just open a book and find, I bet you if you look on the internet, you also probably find this exact problem, to be honest, okay, where you have two loads along a beam. Okay, now, I see people are still thinking or writing. Let's go ahead. Yes, Jonathan?
Maybe you're going to go over this later, but how would this translate if we have like what we had in the second question of the homework, where it's not a force but a moment?
Oh yeah. Okay. So so there are tables that have moments, okay, on them, and sometimes. So how do you say this? When you have, this is not an indeterminate problem. This is just doing superposition. Okay. Yeah. If it's just a determinate problem, it's really nice to do superposition like this. Okay. This may not look friendly, but this is at least a determinate problem. What do I mean by that? I mean, there is no constraint I can take away from the system and still have it be stable, right? If I change that wall to a pin, whoop, right? It's just gonna topple over, right? So this is a determinate problem. I can solve for the internal bending moments and internal shear forces purely through equilibrium. And so this is a nice technique. It gets a little bit trickier to use superposition with indeterminate systems. Okay, it does. Okay, so let's so this is the final answer because we can kind of make an approximation here, and we'll go from there. The approximation is that sine of a very small, the small angle approximation essentially is that sine of a small number is just that small number. Okay. And you can kind of see that these are going to be small numbers in most cases. Why? Because you've got E, which is 10 to the minus 9, right? And I is like 10 to the minus 5, 10 to the minus 4. But anyway, these end up being small numbers. Okay. Here is another table that we might find useful in a second for deflection of a beam. So what is this table looking at? This is looking at a simply supported beam with P. I guess I don't know if it actually probably won't let me erase that out. But that was just me in a prior class putting, this is the internal shear force at the left end, right? And how that's going to be equal to whatever that load is on this end, right? As I get close, or I'm looking at how V, the internal shear force, might vary as a function of length, right? But this approach allows us to essentially change the A and the B, all right? So in this case, they say it's at 0.8. They're showing it's at 0.8, the length of the entire beam. But if you look at these equations, right, you just have something 0, then less than A, and then you have A, less than X, less than L. So you can move this point, or the load P, which is marked as being at point B, back and forth, variably speaking, okay? So if I want, to know what the resulting deflection is and I have my load at the middle and I want it at the middle, right, then I can figure that out. That would be a situation where I'm at X equals A, so I would pick this top equation and I would say that A is equal to, X is going to be equal to A, and those are going to be equal to 1/2 L as I put them in, and B, right, will also be equal to 1/2 L, right, because it would be halfway across. I always felt, not always, but I often felt that the last lesson when I had a class was like usually a little bit out there, and I hope that it wasn't on the exam. All right. There will be a modest question, okay, based on these principles. And that's usually what the professors do. Okay. Modest. Okay, so here, let's take a look at this problem. Two loads, P and Q, superposition, all right? So I've got a deflection at the middle due to P, and I've got a deflection, okay, due to Q at the middle, right? And I add those together. Both of these problems, right, involve sub-problems. They involve determinant systems, right? I can't remove any of these constraints on the ends and not have this thing just go whoop, fall over. So I'm going to go through this quickly because we got stuff to talk about, all right? But this problem, it's pretty straightforward. At least I think more straightforward than the last one, in that we've got to plug in the appropriate L/2 for B and the appropriate, nope, not the L/2. We need to, because this load is here, okay? So we have to think about where now our interest deflection. So the X is beyond the A, okay? Where we are, our point of interest is at L/2, but the P, all right, the A itself is only L/4. Okay, so you see that? So A for this first one is at L/4. Okay, B is 3L/4, and X is equal to L/2. Okay, and then this delta 2, that one's pretty straightforward. Okay, because this one is just going to be the L/2, and you could plug that in to the top one if you wanted, or you could go ahead and look at the W max as well, because that would be halfway across. Okay. And so we can add these together, and this is the result. All right, so this one I think is a little bit more straightforward, although it's more algebraic in nature. Okay, now, indeterminacy. This is going to be significantly, I think indeterminate systems are significantly more difficult to understand, harder to understand. Okay, so remember that when you have an indeterminate system, the number of unknowns is greater than the number of equations that you have. A determinate system is the opposite. Okay, you have nice balance and equilibrium. It's just like equilibrium means more than just equilibrium of forces. Because, of course, in the indeterminate system, you have equilibrium. But it's just so nice that equilibrium does everything that you need it to do. Unfortunately, the real world is not about equilibrium. Well, it's not about only determinate systems. Okay? So we can use those equations to figure out exactly what the external reaction forces are, and we can also figure out what the internal ones are. For an indeterminate system, okay, we're going to see that we're going to have, how many unknowns do we have here? We have 3. unknowns, the external loads. We don't know them, and how many equations will we have that are relevant? We will have just 2. Okay, it means that we can't solve for all 3 unknowns. So this is indeterminate. And the other way to think about it, of course, again, is to just remove one of these. If I can remove it and it still doesn't fall over, then it's going to be, that will now be another determinate. Well, it could be another indeterminate system, right? But it is indeterminate at the start because I can remove one of the constraints and not have it fall over. Okay? Good. How many degrees of indeterminacy do we have for the following? So here I can remove the vertical force constraint and also the moment constraint at the right end, or the same thing I could do at the left end, right? So this one is going to have indeterminacy of degree 2. Okay? So we remove the right or the left wall, and if we do that, okay, we still have we can have a not falling over system, and the right wall had 2 reactions, so it's 2 degrees of indeterminacy. Okay. Here, okay, let's go to this next one. How do we convert it to a determinate system? Well, we could remove this one. Sure, we could remove that one, right? This would just be overhang. We could remove this one too, right? Sure, that would be overhang. We could remove this one too, right? That would also be just a wall supporting all 3 of those point loads, right? So this has degree 3 degrees of indeterminacy. And this one, okay, so we can remove this one, we can remove this one, but if I remove this one, whoop, it falls over, right? So this has indeterminacy of degree 2, okay? So 2 degrees of indeterminacy. I think it's simpler to think, once you look at these a little bit, I think it's simpler to think of, okay, what can I remove and not have everything fall over, than to go through the equations and figure out, okay, I've got this many equations, I've got this many unknowns, what's going on? Okay, but choose the way you want to solve it, all right? Now, method of integration for indeterminate beam, okay? Basic idea, keep on plugging, use continuity conditions, and go forth and prosper, okay? So here, and I have one already online for you, so you'll see this method. You first want to perform external equilibrium and then get frustrated that external equilibrium is not enough. Okay? It can't be enough if it's an indeterminate system. You're not going to be able to solve everything. So that's what happens here. We get frustrated that we can't figure out what all our unknowns are. We have RA, RB, and ML, and just cannot. We need to explore other options. Okay. So in order to solve this type of problem, we can go forward and write some expressions for the bending moment and the shear force that do not have all unknowns in them, right? We can keep track of these unknowns. And then we have to link to the constitutive relationship of primary concern where we have EI, second derivative of V, with respect to X, is equal to the bending moment. Okay. So here is an expression for the internal bending moment, and I have an unknown in it. I don't know what RB is. Okay. I can go ahead, here's my constitutive equation, and I can write that out, just setting it equal to there, and then we can do an integral, and it's an indefinite integral, so we're going to have a constant there. We could do another integral, okay, and then have 2 constants there, right? Or we can, look at boundary conditions even here and say, oh, look, the slope coming out of this wall is 0, right? And so that means that, C1 will be equal to 0 because at x equals 0, the slope is 0, right? So there are different ways we can attack this problem. So at x equals 0, we also know that the v, not just the slope, C2 is equal to 0, okay? And then we can also say at x equal L, we know that the dv dx is equal to 0. Okay, and no, I don't. Oh my goodness, I do not agree with this. Okay, the slope here does not have to be equal to 0 at x equals L. Last. Okay, so once again, you see that I or any of us can make a boo-boo. All right, so this is a case where no, this is not correct, and I'll send out a correction on this. Do you see what I'm saying here is that this at x equals 0 dv dx is going to be 0. That's coming out straight. Okay, and when that's the case, then we just have c1 equal to 0 like that. And since c1 is equal to 0, okay, then that means that the resulting expression that we have is just going to be 1 over EI okay, and it'll be 1/6 RB x cubed minus 1 over 24 W naught x to the 4th, okay, like that. Yes, we can say that at x equals L, V is equal to 0. Okay, so that we can solve, all right, and then we can solve for RB because RB is unknown. So I'll say this part no, but this yes. Okay, RB is unknown, so we use that relationship right there. Okay. I'm just going to skip that because I don't trust this stuff now because these things are not correct. Man, that's unfortunate. Okay, so for question number 2, and this video is already posted, you can take a look at how you can use the integral method to solve for the deflection across the beam and then the displacement specifically at the middle of the beam. The answer is actually already there for you as well. So, method of superposition for indeterminate beam. This is tricky stuff, okay? So we need to satisfy the boundary conditions and we need to use tabulated values. Okay? And for that, we will have these situations where you have, for example, removing one of the extra constraints, but then saying what is that constraint really applying to the system? It's just applying a force P. Okay? And what is the overall displacement at the right side of this? If I'm looking at some type of expression, what is the displacement here vertically? 0, right? So that means that this displacement plus this displacement has to equal to 0. Okay? So we can say that since they're in opposite directions, better said, right? Delta 1, if I say that's going positive, or if I could have said delta 2 minus whatever delta 1, either way, these are equal to each other. And that's because of this geometric compatibility that we have to hold on to. The delta 1 comes from a table, okay? So that's just this value right here. This delta 2 just comes from the table for PL cubed with the PL cubed over 3EI. So now, what can we solve for? The unknown here, well, delta 1 and delta 2, right? We don't exactly know what they are, but we know that they are equal to each other, so they knock each other out. The unknown is the P. We don't know what P is. Okay? So now we can solve for P. And P will be equal to this expression that we have here. And now we can go about trying to solve for the deflection at the middle by using these two representations and using other tables that have described what the deflection at the midpoint is. Okay, other values from the tables. So from the tables, we have that delta M1 is equal to that. and delta M2 is going to be equal to that. And in this case, we can plug in x equals L over 2 directly for both of them. And that will give us the resulting value that we want. Okay, so we plug in for these. Okay, and then we can add them to each other. Any questions on this? Okay, so that the resulting delta M, well, it's already here, right? It's this minus here, okay, of this guy, plus the delta M2 from this guy with x equal L over 2 from both of them. Okay. Whew. All right, question number 3. There's a solution out there, and I'll have a video for you all as well to be able to handle this type of problem. Okay. And the last part is just to think about beams as springs again. Okay. And for this, remember F equals K delta. Okay, and we have rules that we can use, springs in parallel, springs in series. Okay. And this is just for a bar, okay, but the same principles apply. So we said they were often coiled devices, but they don't need to be. This is just copied from session 3, so I'll burn through this. Okay. And this is from session 8, all right? And this was when we were learning about bars, okay? And remember what we said is that P is equal to K delta, right? This is the only thing that we really need to know. But we had this more complicated expression that related the displacement, okay, of B to A, or the deformation, and that was PL over EA. So what is the K? And this, with this equation, with this bar, what is the K here? What's the spring constant for this bar? Yes. That's right. Okay, that's it, right? Because you saw that we have force times, our force is equal to K times the delta. So it's got to be, K has got to be the EA over L. Okay. So that's what we have here, and that's the same principle we're going to use for this type of system. Okay? You see, if I know what the displacement is, okay, from this equation, say at the end, PL cubed over 3EI, I can say that P is equal to K times little v, and so now I know that my K is equal to 3EI over L cubed. Okay? Because it's just the rate, it's just the constant that relates the force and the deflection to each other. So we can begin to look at other situations where we say, oh, hey, what's this effective spring constant? And this is an example that we've done previously. And now here's another table that's maybe a little simpler to understand, where we have P acting in the middle and L over 2. And so we see here that the deflection is PL cubed over 48 EI, which just means that the spring constant is going to be the 48 EI over L cubed. Okay. That's it. That's it for springs. I have one more example, but I'll skip that because I do want to spend a few minutes going through a review. All right. So what we've covered today is how to use superposition, how to use superposition potentially with indeterminacy, but also how to basically handle indeterminacy. Okay, when we're doing a couple of intervals with the EI times the second derivative of the displacement with respect to x is equal to m. And we've also just discussed how we can think of beams as springs mathematically. Any questions? Any questions? Any comments? Okay. If you have questions, send me some notes. You can take a look at some of the previous exams. They will have some tidbits on superposition, some tidbits on indeterminate systems. Okay, and again, my recommendation is to start with the most recent exams first and work your way backward. Now, let's just talk about the class overall and kind of some of the things that we have covered. And to do that, let's just go through the syllabus. And I'll just try to write down a few notes here. Okay. So at this point, I think everybody is familiar with units. Okay. Hopefully also with scaling relationships. And scaling relationships can refer to linearity, right? And superposition. And that may not be exactly how we covered it in that first session, okay? But if I double the applied force, then I double the displacement I'm going to see in my system, right? If I double the applied loads or the torques, I'm going to see double the shear stress if it's a torsion problem, or I'm going to see double the bending stress, okay? Or I'll even see things that we discussed on the sigma 2, sigma 1 plot, or sigma 1, right? Remember, this is going back just a little ways. Okay, remember we talked about how you could have something that looks like this, right? That could be for Tresca, or it could be for modified Moore, right? If these points are, if it's not symmetric, it would be the Moore failure criterion, right? And if I had a point in here of concern, right, I can assume that the load, it was zero stress in the system when I had no load on the system. And so if I were to continue stressing the system, I could form the line, right? This would be linearity. And I could then think about, okay, where is my intersection, right? To figure out what the safety factor is. So that's kind of, that might be a bit of a stretch, but that is an example of relationships that scale. Okay, and it goes to the very end. The units, I don't know what to say. Please keep track of them. Okay, what are the common units that throw everybody off? Well, the elastic moduli. You tell me, on what order are the elastic moduli? 10 to the 9th what?
Pascals.
Right, so 10 to the 9th pascals, and I'll even go further, and it's really like 10 to the 11th, okay, often because we're at 70 or we're at 210 gigapascals, right? So we are like, this is like 10 to the 9th to 10 to the 11th pascals. Yield strengths, what order of magnitude are we? 10 to the 6th, right? 10 to the 8th, right? No, but I'm right with you. So I would say 10 to the 6th to 10 to the 8th, right? And so prefixes, giga. Prefixes, mega. Okay? Please don't write a small m, okay? Please write a small k, though. All right? So, just because we got to be clear, right, with the units and the prefixes that we keep track of. Poisson's ratio, dimensionless. Strain, dimensionless. Okay, keep those things in mind as well. Modulus of toughness, modulus of resilience. I don't know if they'll come up, all right? But what are the units for them? Anyone remember? Okay. Well, what do they represent? Modulus of toughness, modulus of resilience, right? Those represent the area under the stress strain curve, right? So something like this. Remember that? This is a linear elastic, perfectly plastic model. Okay? Well, if I need area under here, the x-axis is dimensionless. Right? So I can take the area under here. It's just going to be the same units as the y-axis. So my modulus of toughness, my ME, my MT, Okay, those moduli are going to be in units of stress as well. Okay. Please remember how to calculate the elastic modulus. Okay, how do you calculate the elastic modulus? Yes?
It's the slope of the elastic region.
It's the slope of that line, right? And if someone gives you this, let's just say they gave you that. How would you calculate the elastic modulus? Yes?
It's also the slope.
No. That would be K, right? The slope here, right, is the stiffness, right? Because that's P is equal to K delta, right? The units. This is force. Maybe I should have specified. This is force versus delta, okay? Of course, the elastic modulus is going to be proportional to this, okay? And I'm leaving out some things here, but we just talked about how we have the K for a bar as equal to EA over L, right? This is for the bar, right? That was a kind of a coincidental thing that we were talking about, beams as springs. So that means that the E will be equal to KL over A, and K is equal to P over delta, right? So that means that we have P, yeah, so that's going to be our PL over delta A. Of course, you have to pick appropriate points, right? But if you know the slope, you can, if you knew the slope here, then you could calculate it this way, or if you know what some delta is for a given P, you can figure it out this way as well. Please be able to do that, okay? Other people in the department think that you're not being taught mechanics when they ask you to calculate the elastic modulus, okay? And I'm like, no, I'm telling you, we've covered this now, okay? In aerospace engineering, okay, so let's go to 2. This is where we can talk about that. Okay, so static equilibrium. Okay. Please, if you're given something that looks like this, okay, what is that? That's a football, right? No, I'm just kidding. All right, it's an airplane, hopefully. Okay, all right. And you have, something like this coming out the back, right? Please understand, if this thing is not accelerating, this is a statics problem. What are the forces acting on this system? Yes. Great. Okay, where are the lifts? I drew 2 sets of wings. Right? Okay, so let's say that we have a center of mass there. Okay? And let's just say we have some FL1 here, and we have back here, we have some FL2. How do you go about figuring out what these values are? And first of all, is this a determinant problem? We're not talking about beam bending. I'm just saying this is just straight up static equilibrium, okay? So how do you do this? How do you do this problem? First you say you're missing, you haven't told me something. I need some more information. What is the more information that you need? Huh? Okay, no, I'm telling you it's a determinant system. What are you missing? You need?
Is it standing on the ground or is it quantum?
Okay, sure. We could add other information to it, but let's just say it's in the air. Help me out. I haven't told you something that's very important, but can you figure out what FL1 and FL2 are? Yes. 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 Okay, you gotta have some reference point. So let's say that this is L1 and this is L2 here, okay? There's a certain aerospace professor who has given this problem to students in the past and then told me they don't know statics. I'm like, well, actually, I don't teach statics, so it's not my problem. No, it is my problem, okay? So, sum of the forces in the y, right, has to be equal to 0. So that's FL1 plus FL2 minus mg is equal to 0. Sum of the moments at a specified location. Let's call the nose O. All right. I also need to know this distance here. All right. So we'll call that the LG. All right. But if I know all these distances, right, I can figure out what FL1 and FL2 are. Okay. It's a statics problem, right? Because here we'll say, okay, I have FL1 times L1, okay, plus, or I'll say minus in this case, minus, okay, mg Lg, okay, plus FL2 times L2 is equal to 0, okay? It's not just tables, it's not just beams, it's not just bars, it's not just trusses, okay? Vehicles obey equilibrium. Now, yes, if it was a vehicle with rubber tires and you have elasticity and I'm like, ah, okay, and you don't know what the displacement is, yes, it can get complicated very quickly, okay, and be indeterminate, all right? But in the air, this is pretty straightforward, okay? Axial loading. Okay, this is what I want to say on axial loading. And then I've got to wrap up, okay? Please, please, please. Okay? If you're given, say, an Fy, that would be the yield force. Okay? First off, you should know that the yield strength is just going to be that F yield over the cross-sectional area. Correct? That should be straightforward. Now, if I say, let's use the criterion of Tresca, maximum shear stress. Okay? What you want to do in your problem is you want to hunt down what the absolute maximum shear stress is. And I think that you're like, oh, that's really easy. I know how to do absolute maximum shear stress. I just figure out what the principal stresses are and I draw 3 more circles and I'm good to go. Please, though, remember that what you are comparing to is also the maximum shear stress in this basic case, right? You don't compare the if I say maximum shear stress theory, Tresca, you got to compare it to something. And if I give you a yield strength, you got to be like, oh, well, now I know how do I calculate the shear strength, right? And so SSY, that's the shear strength, is half of SY. How do I know this? How did I just do that calculation so fast? Well, 1, I remember it. But 2, how would you do this? Anyone? Help me out. What is the equivalent maximum shear stress in this situation? Yes. No, that's a loading question. That's a transverse shear stress on the cylindrical cross section. I'm looking at this one right here. Yes. It's another more circle. And this is where we will end. Right? This is a state of principal stress. This is out at SY. Remember this? Sigma 2 and sigma 3 are equal to 0. They're at the origin. Okay? Sigma 2 equals sigma 3 equals 0. That's here. So now I draw my Mohr circle. And what's my absolute max? Which I'll call R. So the radius is equal to the SSY, which is equal to 1/2 SY. Okay? This is pretty important. Okay, because every test, every material that you ever use in an engineering application, I'm not talking about when you go to Home Depot, you're like, hey, or Lowe's, or whatever shopping store you go to. You're like, hey, I just need to support this thing. I get a couple 2x4s and it's going to work. No, I'm talking about in an engineering sense, you're going to get material specs. Every one of those material specs, virtually every one, will have the yield strength of the material. But virtually all the ductile metals fail because of Tresca. Okay? Or you use von Mises, right? So then you're just looking at SY, but you should remember this. No more writing, we're done, but pointing out that the things that we have not covered are sessions 20 to 25. Those are the 6 sessions. The exam, yes, is it cumulative? Yeah, but I think there's going to be more emphasis on the more recent things. It's been a pleasure to be with you this semester. I hope that some of the importance of what we're talking about has come out even more than some of the math. And I look forward to seeing you guys in a week. Let's give you the final attendance. Which again will be wonky. All right, but that's okay. We'll just do it like this. All right, and we'll make it big. All right, just like that. All right, great. Thank you, everybody.